My presentation is on ISAR imaging of boats using low-cost, off-the-shelf hardware. This project is actually a continuation of my team's entry to the IEEE Radar Conference's Radar Challenge. And the premise of the challenge was to find creative ways to use the CN0566, a low-cost radar kit from Analog Devices. And yeah, just find compelling ways to use it. So here's a picture of the CN0566, the radar kit from Analog Devices on the left. And you know, there are a variety of reasons to care about using a cheaper and smaller hardware, not the least of which is money, portability, and power requirements. The radar kit used in this project costs less than $3,000. By contrast, the other radar systems that I regularly get to work with cost an eye-watering amount of money that I won't say aloud, and took a whole truck to transport to the site it needed to be at, and it also tripped the circuit breaker that was in my lab. So I think there's a compelling case for trying to do real field work with these low-cost, off-the-shelf systems. And I think the most compelling project that we could do with this is ISAR, or inverse synthetic aperture radar. With inverse synthetic aperture radar, we can see what passing boats look like, even in pores of visibility, such as in fog and at night. Additionally, it can be set up in a variety of places because the radar is stationary, and so it doesn't need a whole bunch of moving pieces to assemble on site. And so, you know, being cheap, lightweight, and only needing 5-volt power supplies to run opens the door for creating something cool like a distributed sensor network. I can envision a network of these sensor kits being used around, say, Lake Union, which is near the University of Washington, where I'm at. And it could be used to monitor water traffic in cases where optical systems would fail. Of course, we need to get down to the basics first. Before I get into the specifics of this project, I want to give some background on some concepts we'll need later on. Firstly, SAR imaging, or synthetic aperture radar imaging, is a technique to get longer apertures without physically building larger antennas. In SAR, the synthetic aperture comes from the motion of the platform. By contrast, the synthetic aperture of inverse SAR comes from the motion of the target. And the cross-range axis of an ISAR image is created by the collection of look angles along the track of the target. Meaning, if we were taking a snapshot of the backscatter field at each T1, T2, T3 labeled in the picture, we would have 3 look angles of our target, and that would translate to 3 pixels on our image. Secondly, our radar was configured as a frequency modulated continuous wave radar. An FMCW radar works by continuously sending out ramp pulses and then listening for the echo to calculate what's called the difference frequency. The difference frequency corresponds to the amount of time it took for a signal to come back to our system, and from that time we can calculate the range. Therefore, we can create the range axis of our 2D ISAR image from the difference frequencies, and we'll talk more about how we get the resolution of our 2D images later in this talk. Now, some more details onto the system we used. So on the slide is a diagram of the radar kit designed by Analog Devices. At a high level, the system is configured to have a theoretical maximum viewing range of 1.8 kilometers, which is about the north-south viewing length of Lake Union. Unfortunately, did not get to measure and test this system rigorously enough to validate that I can actually see out a full 1.8 kilometers, but that's in the pipeline, and anecdotally, I was able to see a row of houses during testing that was about 450 meters away. There are also a few things I want to note in this diagram, so I'm going to walk through the signal chain. First, our Pluto SDR's transmit local oscillator has been set to 2.15 gigahertz and also mixed with a positive 500 kilohertz to create a DC transmit tone, which we'll use later in this presentation. The transmit signal is sent through the low-pass filter and then mixed with the phased array's local oscillator, which is chirping from 12 gigahertz to 12.5 gigahertz. We keep the different side of the mixer output due to the low-pass filter, so out of our antenna is a 9.85 to 10.35 gigahertz chirp. Our receiving patch antenna hears the return chirp and sends that signal back to be mixed with our local oscillator again to get the beat frequencies. And a special configuration note that we had to do make with this project is that we changed the chirp range. So normally out of the transmit path is Analog Devices recommends a 10 gigahertz to 10.5 gigahertz chirp, but as you can see in the figure, our relative power of response had a lot of rejection near the end of our band. This limited our range resolution and caused problems with our within buffer phase coherence. And so to avoid this problem, we brought our RF chirp ranges down. So now with these settings, we were reliably able to get good range information of targets on the water, and so we can start pre-processing our data. Without pre-processing, our images will be extremely blurry and out of focus. To correct the phase of the ramps within a data capture, we found the phase of the 500 kilohertz DC path to use as our phase reference. Then we simply shifted the phase of each ramp to match our reference phase, which gave us 3 coherent ramps. As a proof of coherence, we averaged 3 chirps, which should increase SNR by 4.8 dBs, assuming Gaussian noise. This improvement is visible in our range plots. Next, I'm going to talk a little bit about our ISAR processing approach. So ISAR works by integrating range frequencies and Doppler frequencies to map out an image. Or in other words, our image is formed by simply using a 2D Fourier transform of the 2D backscattered data. More specifically, this means taking the Fourier transform of our stretch process beat frequencies to map our range profile from a single chirp. Additionally, taking the Fourier transform across chirps with aligned range bins gives us a 2D range Doppler map. A vessel's rotation Doppler frequencies are equivalent to the vessel's cross-range profile at that instant. The negative Doppler frequencies correspond to the end of the vessel rotating away from the radar, and the positive Doppler frequencies correspond to the end of the vessel rotating towards the radar. And then another thing to note is that our resolution of the images is determined by both the radar hardware and the motion of the target. In our system, we have a 500 megahertz ramp, and we can find that our range resolution is equal to the speed of light divided by 2 times the bandwidth of our ramp. This translates to about 30 centimeters of resolution in the range dimension. Meanwhile, we can find our cross-range resolution by understanding the synthetic aperture created by the motion of the target. Our receiver had about a 13-degree beam width, and without beam steering, the synthetic aperture is limited by that beam width. So knowing our center frequency of operation is about 10.1 gigahertz, we find the best case cross-range resolution of our system to be 6.6 centimeters. Another important component of ISAR imaging is doing the appropriate motion compensation for our data. We want our target features to be aligned when we integrate our backscatter data, so that means we need to do range compensation. In this slide is an example of how to do how range compensation works. In this data set, the track of the vessel was given by GPS data, and the track was inverted to align the range bins of the data. Unfortunately, we don't always have GPS data to work with, so to perform range correction on targets where we don't have that data to figure out their range, we need to use a tracking algorithm on our backscatter data. We opted for a conceptually simple tracking method, which was proposed by my mentor at the Applied Physics Lab, John Mower, as a rough and quick way to implement getting our range tracks. The idea is that we roughly know the shape of a flyby range plot will be an arc. I approximated this arc by assuming the motion is similar to a third-order polynomial and exhaustively searching within a limited space of parameters the best matching third-order polynomial. The matches were scored by integrating the backscattered energy along the proposed track. A low integration result would imply the track was not well aligned on our target, while a high integration result would imply the track is following the target well. An example track generated by this method can be seen in the slide. So using this range tracking method, the following images were generated. The first one is of a tugboat that happened to be passing by while we were doing field testing. And the second one is of the research vessel from the Applied Physics Lab, the RV Lee Thompson. Something to note about these images is that I tried to integrate over a much larger angle than is typically accepted for a small angle system. These images were made using the full 13-degree angular width. Normally, that would trigger the need for us to do cross-range alignment, but I found that surprisingly, the blurring didn't completely wash out my images. You can still make out the specular highlights of the gantry pillars on the boat, and the dimensions for the vessels, which were outlined in red in the images, were pretty well matched to the shapes that we see in the ISAR images. So that means our images do still make some sort of sense, but still, I think these images would have been made better if I had done the cross-range corrections. In the future, if I can get some ground truth figures on the heading of our vessel, I'd like to investigate making a tracking algorithm for the phase correction. So in conclusion, this project proved that you can use low-cost, off-the-shelf radar systems to perform ISAR imaging on vessels on the water. And this slide is a summary of the final system parameters we used during testing for anyone attempting to recreate the system. And on its own, this project doesn't look like too much now, but the accessibility of these radar kits really opens the door to more advanced projects. To call back to the beginning of this talk, I believe in the potential of using these radar kits for a distributed radar system. There are several other directions we'd like to take this in the future as well. The first would be expanding into more complex motion compensation algorithms and autofocusing. As mentioned before, I'd like to investigate using heading tracking, which I believe would also unlock the ability to image vessels with more complex motion patterns. And there's also wake detection. Because our receiver is vertically polarized, we are set up well to be able to image the water surface. Then we can create detection algorithms to find wakes from passing water vehicles. The Applied Physics Lab has a long lineage of work involving wake detection and wave reconstruction, so our group has a lot of interest in this subject. So we see potential for wake sensing in even our existing waterfall plots, where we almost seem to see a point spread at the bottom of the plot on the right there that doesn't quite follow just being simple range migration of the target. All in all, I think there's a lot more fun to be had with these kits, and I'll have my hands full for a while yet. But that's all from this talk. Any questions for me?